Hello, welcome to this 17th lecture session of the course Database Management Systems. In the previous session, we discussed about the schedules, serial schedules, concurrent schedules, and we understood what are the advantages of concurrent schedules and what are the disadvantages. The advantage is a concurrent schedule can increase the throughput because the various data items or the resources can be shared by multiple transactions, and at the same time the ill effect due to this concurrent execution of the transactions is that, and that may lead to inconsistency problems because multiple transactions are trying to access the data items at the same time. That may lead to some problems. In this session we discuss the basics of concurrency control and implementing serializability and lock based protocols, deadlock conditions and the mechanisms to avoid deadlock or come out of the deadlock, two-phase locking protocol and timestamp based protocols for achieving mutual exclusion, which provides the serializability in concurrent schedules, concurrent execution of these transactions. We know that in a database management system, multiple transactions are executed concurrently. If the transactions are executed concurrently, then the resources can be utilized more efficiently, hence more throughput can be achieved. Here for transactions we consider data items as resources because transactions process data by accessing them. When multiple transactions access data elements in a concurrent way, this may destroy the consistency of the database. Hence for concurrent schedules we need to be careful. One way of ensuring serializability, that is, we understood that a serial schedule is always leaving the database in a consistent state or correct state. Similarly, a concurrent schedule which is a serializable schedule, meaning that the concurrent schedule whose result is same as executing the transactions in a serial way is known as a serializable schedule. A serializable schedule is more desirable and that will also leave the database in correct state. Hence a serializable schedule is more desirable. We enjoy the concurrency, at the same time we will not have any problems with respect to concurrency. One way to ensure serializability is to allow the transactions to access the data items in a mutually exclusive manner. What do we mean by this mutual exclusion? And this says that this is to make sure that when one transaction accesses a data item, no other transaction can be accessing the data item for the purpose of modification. That is, at a given point of time only one transaction can access and modify the data item, and this is called as mutual exclusion. For example, if you look at this transaction, how we can achieve serializability by locking. I have two transactions T1 and T2, and it is a very simple schedule where each transaction has only two instructions. This reads data item A, immediately T2 reads data item A, then write A and then T2 writes A. And if you carefully observe, this is not a serializable schedule because the swapping of any, that means this is a pair of conflicting operations and this is also a pair of conflicting operations. Hence I cannot swap this so as to make T1 and T2 a sequence or T2 or T1, so which is a serializable. That since that swapping is not possible, here in this case the schedule is considered to be a non-serializable, or it is a concurrent schedule which cannot be serialized. Then the problem with this is when you execute this, this may leave the database in some incorrect state. Then what I can do is to make this serializable, that is, to make the effect same as executing T1 first and then T2 next, what I can do is when T1 wants to read or access the data item A, then it can acquire a lock on data item A in exclusive mode. When it is in exclusive mode, a transaction can read the data item or modify the data item. Once the T1 has acquired a lock on data item A, no other transaction if it wants to access that cannot do that because the lock has been already acquired by some other transaction. The other transaction has to wait till the lock on that particular data item on which it is waiting is released by some other transaction which is already holding a lock on that data item. So in this case, if T1 applies a lock on data item A here and then proceeds with reading or manipulating with the data item, then immediately when this fellow wants, the T2 wants the data item A in read mode, it cannot acquire a lock, it cannot access it because it is already locked by T1. And if we assume that after completing its activity or the operations, if T1 releases the lock on data item, then the waiting transaction, that is T2, can get a lock or can access the data item A and can proceed further. And this is same as executing the instructions of T1 first and then executing the instructions of T2 next. This is how, using locks, we can achieve serializability. Apart from this locking, we have other techniques are also available, and let us see what are the techniques that can be used for mutual exclusion. The first technique is based on locks, it is called as lock based protocol. The second technique used for achieving mutual exclusion is timestamp based protocol, okay, where we will be using various timestamps that we will discuss in the next few slides. Hence, to achieve mutual exclusion, we have lock based protocols and then timestamp based protocols. First, we will discuss the concurrency control using locks. A data item may be locked in various modes, shared mode or exclusive mode. If it is locked in a shared mode by a transaction, that means if a transaction obtains a shared mode lock on a data item Q, it can read the data item Q, but it cannot modify the data item Q. And if a lock has been acquired in exclusive mode, a transaction can read as well as write the data item, that is, it can perform read operation as well as write operation on the data item if it acquires a lock on the data item in exclusive mode. Okay. Now, let us have a look at this lock compatibility matrix. Let us assume that there is a transaction T1 which acquired a lock on a data item in shared mode. Then the other transactions, they can acquire a lock on the same data item in shared mode, but no other transaction can acquire a lock on the same data item in exclusive mode. Similarly, if the transaction T1 has acquired a lock on data item A in exclusive mode, then the other transactions cannot acquire lock on the data item either in exclusive mode or in shared mode. That is not possible. So, this is the lock compatibility matrix. This says that if a transaction Ti obtains a lock on a data item in shared mode, other transaction can get a lock on the same data item in shared mode only, but not in exclusive mode. If a transaction obtains a lock in exclusive mode on a data item, no other transaction can obtain a lock on the same data item in any other mode, meaning either share or exclusive mode is not possible on the data item if it is locked in a exclusive mode by some other transaction. Now, when you have this kind of mutual exclusion, that means one transaction locks a data item and another transaction wants the data item for manipulation, then the other transaction has to wait on that. That is, it is because it is mutual exclusion mechanism, only one transaction can access or enjoy the data item. And under this situation, it is possible that it may lead to deadlock condition. The mutual exclusion mechanism leads to deadlock situation. Now, let us see what is a deadlock situation. If transaction Ti holds a lock on data item Q in exclusive mode and waits for a lock on another data item P, which is actually locked by another transaction Tj in exclusive mode. Further, to release the lock on P, Tj must acquire lock on Q, and which is locked by Ti, and this is a circular wait condition and results in a deadlock situation. Now, let us have a look at some example which clearly explains or describes this situation. We have this schedule which has two transactions T1 and T2, and these are the instructions of transaction T1. It has 6 instructions, and T2 has the following instructions, that is 6 instructions are available. First, T1 locks data item A in exclusive mode, then immediately T2 locks data item B in exclusive mode. Then T1 proceeds with processing data item A, and now immediately it wants to access data item B in exclusive mode, but it cannot be here. There is a block situation, because the transaction T1 cannot proceed because it wants to acquire a lock on data item B in exclusive mode, the data item B is already locked by transaction 2 in exclusive mode. So hence this T1 blocks, it cannot continue further, automatically the control will go to T2, and T2 will proceed with the second instruction. That means it processes B, and immediately as part of its third instruction it needs a lock on data item A in exclusive mode, but it cannot acquire that because here the T2 blocks, because it requires a lock on A in exclusive mode and the data item A is already locked by transaction 1 in exclusive mode. And in this case what happens, when T2 can acquire the lock on data item A, when it is released by T1, and when T1 will release the lock on data item A, when he acquires a lock on B, and then once he completes his process, then only he can release the lock on A. And similarly, after acquiring a lock on A, once it is done with its processing, the transaction T2 will release its lock, exclusive mode lock on data item B. Now what happens, and I can draw to see whether there is a there exists a deadlock situation or not. I can consider this waiting queue, wait queue, otherwise I can call it as a wait queue, transaction wait queue for data items. I have data item A, I have data item B. Now as a first instruction, what is happening, T1 is locking data item A in exclusive mode, then it processes A, and then immediately that T2 is locking data item B in exclusive mode. Then as a third instruction, T1 wants a lock on data item B in exclusive mode. That is why T1, it cannot acquire it immediately because it is already held by the transaction T2. Hence T1 has to wait in its wait queue for data item B. Now immediately control goes here, the process B happens, and then T2 wants a exclusive mode lock on data item A, but it is already locked by the transaction 1 in exclusive mode. Hence T2 will have to join the wait queue for data item A. And if you see that there is a circular wait, that is T1 is waiting for some resource which is to be released by T2, and then T2 is waiting for some resource which is to be in fact released by T1. So there is a circular dependency, and then circular wait condition is there, and this is known as the deadlock situation. And this deadlock situation is result of mutual exclusion. If I don't have this mutual exclusion, and then both the transactions can access the data item freely, but there is a problem of inconsistency. That is, if mutual exclusion is not there, there is no deadlock situation, but there is a problem of inconsistency. But mutual exclusion is imposed, then the inconsistency may not be there, but there is a problem with deadlock situation. Okay, instead of getting into inconsistent situation, it is better to face a deadlock condition. In some cases, of course, it is not true in all the cases, but most of the cases, instead of having an incorrect database state, it is better to actually encounter deadlock situation and try to resolve that in a proper way. Now let us discuss a mechanism, a technique using which we can detect the deadlock condition in a given schedule. And we use the graph called as a wait for graph. It is called as a wait for graph. And what is this wait for graph? It contains nodes, edges, and nodes are nothing but the transactions that are involved in the schedule, and we can introduce an edge from transaction Ti to Tj if Ti is waiting for some resource which is locked by Tj. So then I can introduce an edge from Ti to Tj, and based on these conditions I can develop the wait for graph, and at any given point of time if I see a cycle in the graph, then I can stop my algorithm and then declare that the schedule will result in a deadlock condition or deadlock situation. Let us have a look at this schedule, which contains T1, T2, T3 and T4 transactions, and the corresponding instructions of these independent transactions are given there, and the y-axis indicates the sequence or the ordering of execution of these instructions from multiple transactions. And SA means T1 acquires a shared mode lock on data item A, RA means the T1 reads data item A, and WB means T2 writes data item B, XB means this transaction, that is T2, acquires a lock on data item B in exclusive mode. Now under this situation, first we will see how to develop this wait for graph. To develop a wait for graph, it is better to have or better to understand which transaction is waiting on what transaction for a resource. For the same transaction schedule given in the PPT, let us see how I can find out what transaction is waiting on what other transaction for a resource. Now the execution starts from here. T1 acquires a lock on data item A in shared mode. I have 3 data items A, B and C, and these are the wait queues for the corresponding data items. When T1 locks A in shared mode, then it is locked by T1. Then immediately it reads A. Then the next instruction that is executed in this schedule is the T2 acquiring an exclusive mode lock on data item B. Hence T2 acquires exclusive lock on data item B. Then T2 is writing data item B. Then the transaction 1 wants a shared mode lock on data item B. Can it get this lock? Because the data item B is already locked by transaction 2 in exclusive mode. Hence T1 cannot proceed further, it blocks here. It is waiting for the data item B, which is locked by T2 and which is to be released. Hence the T1 will join the wait queue for data item B, which is locked by T2. Then since it is locked, immediately the next instruction is this one, that is T3 wants a shared mode lock on data item C. So T3 locks data item C in shared mode. Then immediate instruction is the T3 reads data item C. Next immediately the T2 wants exclusive mode lock on data item C, but it is already locked by T3 in shared mode. Once one transaction locks a data item in shared mode, no other transaction can acquire any kind of lock on the same data item. Hence the T2 cannot proceed further, it is blocked, and now it is in the wait state for the data item C. Hence T2 is joining the wait queue of the data item C. Both T1 and T2 are blocked. Next instruction that is executed is now T4 wants an exclusive mode lock on data item B, but B is already locked by the T2 and it is not yet released. Hence it will go to the wait state or blocked state, and T4 is added to the wait queue for data item B, which is locked by T2. And since T1, T2, T4 are already blocked, they cannot continue further. The next transaction instruction that is taken up is the T3's instruction, that is it wants to acquire a lock on data item A, which is already locked by T1 in shared mode. Because it is locked by T1 in shared mode, T3 cannot acquire a lock on data item A, and T3 will join the wait queue of data item A, which is locked by T1. Now if you carefully observe, now here it blocks all the transactions. How many transactions I have in this schedule? I have 4 transactions. After reaching this point, let us assume that there are further instructions available in the schedule. After reaching this particular point, all the transactions T1, T2, T3 and T4 are in blocked state. That means they are holding some lock on some data item, and at the same time they are waiting for some data item which is already locked by some other transaction. Now the schedule cannot move further, that is no instruction of the schedule can be executed further. Now it is called as a deadlock situation. Now let us develop the wait for graph for this situation and see whether we can see cycles in that or not. Now this is the wait for graph. What become the vertices of this graph? The nodes, they are nothing but the transactions that are involved in the schedule. I have T1, a node for T1, a node for T2 and a vertex for T3 and for T4. Next, when I can introduce an edge between Ti to Tj, when Ti is waiting for some resource which is locked by Tj, then I can introduce an edge from the node Ti to Tj. T3 is waiting for some resource which is locked by T1. So, I have an edge from T3 to T1, this is the one. Next, T1 is waiting for resource locked by T2. So, T1 to T2 I have an edge. Similarly, T4 is waiting for data item B which is locked by T2. That is why T4 to T2 there is a edge. And T2 is waiting for a data item C which is locked by T3. Hence, I have an edge from T2 to T3. Now, if you carefully observe, there is a cycle. There is an edge from T2 to T3. From T3 to T1 I have an edge. From T1 to T2 again I have an edge. So, it is a cycle. Hence, there exists a cycle in the wait for graph. Now, I can declare that this will lead to a deadlock situation. Okay, so, this is how we can find out whether a given schedule results in a deadlock condition or not. The same thing has been represented here. This is the wait for graph, and same thing we have seen there in that diagram. So, there exists a cycle, hence it is deadlock prone, that is it will result in deadlock. Now, in the above graph there exists a cycle, hence the schedule leads to deadlock. If a transaction Ti requests a lock and transaction Tj holds a conflicting lock, the lock manager can use one of the following policies to prevent the deadlock situation. That means there are two transactions, that is this is T1 or otherwise this is Tj, and then the Ti is the transaction which is making a request for a lock which is already held by the Tj, let us assume like that. So, what kind of policies will be adopted to resolve this deadlock situation? That means when a deadlock occurs, what should happen, and we need to abort or we need to stop execution of a particular transaction, so that and it will release the lock on a data item, the other transaction will continue. We need to interrupt a transaction. And what kind of approaches or mechanisms are available to find this or to avoid this deadlock, to resolve this deadlock? First one is based on timestamps. The second approach is based on the priority. In the timestamp based protocol, every transaction will be associated with the timestamp. That is, let us assume that whenever a transaction starts, the time during which it has been started can be used as a timestamp in milliseconds, whatever it is. Okay. So, if the timestamp of T1 is less than timestamp of T2, it means that T1 is the older transaction and T2 is the younger transaction, because T1 is the first one to start. Then if that is the situation, if Ti wants some data item which is locked by Tj, and if Ti is older than Tj, it is allowed to wait. If Ti is younger than Tj, then it is aborted. That is wait and die approach. If it is a older one, it will wait. If it is a younger than the transaction that holds a lock on the data item, it is aborted. The second approach is wound and wait. If Ti is older than the Tj, that is this Ti which is making a request for data item which is locked by Tj, if it is older, then it will older than Tj, it is allowed to run by aborting Tj. That means it will wound Tj. That means we will abort Tj and allow Ti to run. Otherwise, that is, if Ti is younger than Tj, it is allowed to wait. This is called as this procedure, this mechanism is called as wound and wait approach. Then we have priority based protocols. Then, like how we have associated timestamps with transactions, we can also attach or associate priorities for the transactions. Okay, higher priority transaction is always given high priority to access the data items, or to at the time of execution it will be given high priority. Under this priority based protocol, if Ti which is making a request for data item locked by Tj, if Ti has higher priority, it is allowed to wait until Tj releases the lock on the data item. If it is not a high priority job transaction, then it is aborted. This is called as wait and die policy. And the other one is wound and wait. If Ti has high priority, it is allowed to run by aborting Tj. If it is not the case, that Ti is allowed to wait. This is called as wound and wait policy. But the mechanism is same, but whereas in the first approach it is based on timestamps, whereas in the second approach it is based on the priority associated or attached with the transactions. This is how a deadlock situation can be resolved by the deadlock or concurrency control module, which is integral part of the database management system. Okay, we have been discussing about the log based protocols, and in the log based protocol another important protocol is two-phase locking protocol. This protocol answers serializability, that means we can achieve serializability. According to this, each transaction issues lock and unlock requests in two phases. That means when it acquires locks or releases locks, it will have two phases, growing phase and then shrinking phase. That means let us assume that there is a transaction T1, it requires lock on A, request for a lock and release a lock, and on B also it requests a lock and releases the lock. Like that it will make a request and then release a lock. If such is the situation, every transaction in this process will have two phases. One is growing phase, the second one is shrinking phase. What happens in the growing phase? In this growing phase, a transaction may obtain locks but not release any of the lock. That means in the first phase, let us assume that there are two phases. In the first phase, independent of when the given data item is required by the transaction for processing, it will keep on acquiring locks on the data items. This is called as the growing phase and then or locking phase, and once it has required, it has acquired a lock on the last data item which is required for the processing. Then once it is done with the first data item, it will enter the releasing phase, unlocking phase, or it is called as the shrinking phase. Once it enters the shrinking phase, it will start releasing the locks which are already acquired during the growing phase, and once it is in shrinking phase, it will not make a request for any new lock. That is, during the growing phase it will keep acquiring locks on various data items that are required, and once it starts the shrinking phase, it will keep releasing the locks which have been acquired on the various data items for that for the processing by the transaction. So in two phase locking we have two phases, growing and shrinking phase. The two phase locking protocol ensures conflict serializability. It ensures serializability, but it does not ensure freedom from deadlock, because there exists some amount of mutual exclusion. Okay, independent of whether you require that immediately or not, you are going to acquire locks on all the data items independent of the time you actually need that. Hence, that will not ensure freedom from deadlock, but it will always ensure conflict serializability. Now let us have a look at timestamp based protocols. We understood that concurrency control is achieved by mutual exclusion mechanism, which can be achieved either by locks, applying locks, or by timestamp based protocols. Now we have finished our discussion on lock based protocols. Now we will discuss the timestamp based protocols for achieving mutual exclusion or for achieving concurrency control. Maintaining the ordering between every pair of conflicting transactions is significant. If we select the ordering in advance, we can achieve serializability. Timestamping is a method to fix the ordering. That means if you have two transactions and if they have some conflicting operations, and if you have the order between these two transactions, let us assume that T1 and T2 are the transactions, and if I have a ordering saying that T1 is first in the order and T2 is second in the order, how can I fix this order? It can be achieved by associating a timestamp with each of the transactions, like the time when the particular transaction has been started, that can work as a timestamp. Okay, so this will fix the ordering. If the timestamp of a given transaction is 5, 6 something like this, and if the timestamp of T2 is 2896, which is this is less than the timestamp of T2, then I can say that T1 is the transaction which has been started first by the system. Hence, in the order T1 comes first and then T2 comes next. If you have this kind of ordering, then it is easy to achieve the mutual exclusion, and we can decide which transaction will access or the data item and which transaction is not properly accessing the data item, so that if it is accessing a data item, it can lead to problems. That kind of situation can be handled by this timestamp based protocol. Let us have a look at the examples, things will be more clearer. Each transaction is assigned a unique fixed timestamp. This indicates timestamp of transaction Ti. This indicates the timestamp of transaction Tj. If timestamp of transaction Ti is less than timestamp of Tj, this implies that Ti should be executed before Tj, because this is the older transaction, this is the younger transaction. Hence, Ti has been started first, hence it should be allowed to execute first. That is the order. Once you have this kind of ordering, then we can resolve the problem. The timestamp determines the serializability order, and similarly, how we have attached timestamps with the transactions, we also associate timestamps with the data values. Each data item will have two kinds of timestamps. Let us assume that the data item is Q and it has two kinds of timestamps. First is write timestamp, second is read timestamp. What is this write timestamp? Represents the largest timestamp of any transaction that successfully executes write operation on the data item Q. What is R timestamp on data item Q? Which denotes the largest timestamp of any transaction that successfully executes read operation on the data item Q. For every data item, we will have W timestamp and then R timestamp. These values are updated whenever read and write operations happen. Let us assume that there is a T1 whose timestamp is 150, 145. There is T2 whose timestamp is 111. Suppose there is a data item A which will have two timestamps, W timestamp and then R timestamp. And if T1 comes and writes onto this data, writes this data item, then the value of W timestamp will be 145. And if T2 comes and reads this data item, and as of now the read timestamp for data item A is 111. Okay. Next, let us assume that T3 one more transaction which has timestamp 163 comes and reads this, then immediately the value of read timestamp for the data item A becomes 163, and if this is going to read the data item, then this write timestamp for this data item A will become 163. That is why every data item in the database will be associated with two timestamps, W and R timestamps. Now let us have a look at this timestamp based protocol. This protocol operates as follows. Let us assume that there is a transaction Ti which wants to read or write on the data item Q. There is a data item Q. Suppose the transaction Ti issues read operation on data item Q. If the timestamp Ti is less than, so Q will definitely contain write timestamp and then read timestamp. Suppose if this is the transaction which has the timestamp 145 and write timestamp is 123 and then read timestamp is 160. Let us assume like that. If the timestamp of Ti, which is 145, is less than write timestamp, that is 123, yes, it is not the case. In this case, what happens? The W timestamp of data item Q is 123. So this is not the case. That means what? The Ti, the transaction which is a younger transaction than the transaction which has already written the data item Q, is now issuing a read operation on Ti. So we do not have to worry. So ordering is, first is the transaction with timestamp 123, next comes 145, hence we can allow it to read. Okay. And now Yeah, if the timestamp of Ti is less than the write timestamp of Q, then what happens? That means some transaction has written the data item Q and whose timestamp is greater than the current the timestamp which is making a read operation, read request. Then what does it mean? An younger transaction, that is the transaction Ti is older than the transaction which has recently written the data item Q. Then in that case the order is Ti first and then that transaction Tj which is which has written the data item Q. So in that case this is the older transaction, hence it implies that Ti need to read the data item Q which was already overwritten by some younger transaction which has been started later, hence it may lead to some problem, hence the read operation is rejected and the Ti is rolled back and then it is restarted. And if the timestamp of Ti is greater than or equal to write timestamp of the data item Q, meaning that the Ti is the younger transaction or the same transaction which has quite recently written the data item Q, in that case there won't be any problem, then the read operation can be executed or honored. So this is when a transaction Ti issues a read operation. Now let us see what happens if a transaction Ti issues a write operation. Suppose if the timestamp of Ti is less than read timestamp of Q. Now the Ti is trying to write and we should look at both read and then write timestamp. If it is a read operation like in the previous case, I don't have to look at the read timestamp of the data item Q, because read and read, they are not conflicting pair of operations. I need to look at only the write timestamp. But when Ti is making a request for write operation, then I need to look at write timestamp as well as read timestamp. If the timestamp of Ti which is making a request for write is less than the read timestamp of the Q, meaning that the Ti is a older transaction than the transaction which has quite recently read the data item Q. It implies that the value of Q being produced by Ti had been overwritten long back by somebody else. Hence the write operation request by Ti is rejected and the Ti is rolled back and then restarted again. If the timestamp of Ti is less than the write timestamp of the Q, then it implies that Ti is older than the transaction which has quite recently written the data item Q. It implies that Ti is attempting to write some absolute value of the data item Q, hence the Ti is rejected and rolled back. If these two conditions are not true, then the operation can be honored. For example, let us assume that I have a transaction T1 and there is a data item Q whose write timestamp is 145 and then read timestamp is 160 and it is 123, and let us assume that this belongs to some transaction T2 and then this belongs to some transaction, the timestamp belongs to transaction T3. Now if he wants a read operation on the data item Q, then I don't have to look at the read timestamp, just I need to look at the write timestamp. You check whether the Ti, that is the timestamp of T1, is less than write timestamp. In this case it is yes, that means the Ti is the older transaction, but due to some reason the younger transaction T2 whose timestamp is 45 has modified the data item, hence the T1 may be reading some incorrect data item, hence don't honor the request, don't honor the request. Suppose if the timestamp is 111 which is a timestamp T10, meaning that when it makes a request for reading the data item Q, then the timestamp of T1 is greater than this one, that means T1 is younger than this transaction T10 which has written the data item quite recently, hence there will not be any problem, then we can honor that request, that means it can be executed. Suppose if he wants to execute a write operation, then what should I do? First check whether the write timestamp is greater than or less than the timestamp of this requesting transaction. 123 is greater than 111. So, there is no problem. It can be, and then you also look at the read timestamp. The read timestamp is greater than the timestamp. That means that quite recently some transaction T3 which has been started late has already read the data item Q. Hence, now if you try to modify the data item, then it may lead to inconsistency. Hence, in that case we will not allow it to operate on that. Hence, in that case we will reject and roll back this. And if these two are the not conditions are not satisfied, then we can allow the transaction to execute. This is how this timestamp based protocols will work. Every transaction under execution will be attached a timestamp, and then every data item which is accessed by transactions will also have two timestamps. One is write timestamp, the other is the read timestamp. Based on this, we will, when a transaction make a request for some operation like read or write, we will look at these two timestamps associated with the data items, and we will decide whether to execute that operation or to reject and roll back that particular transaction. In this session, we discussed about concepts related to concurrency control, approaches for implementing serializability, that is lock based protocols and then timestamp based protocols. How lock based protocols work, and then we have also seen what is two phase locking. Then we have seen the wait for graphs which are used for detecting the deadlock condition in a given schedule. We have also seen how to resolve or get away with this deadlock situation. We have seen two phase locking protocol, and at the end we have seen how timestamp based protocols work with the data items and then various transactions trying to access the data items. Thank you very much.